Hey everybody, welcome back. This is 12.3 in Calculus 3. It's the fall semester of 2022 at College of the Sequoias. 12.3 is on changing parameters in our vector functions. Let's just jump right into it. So far, we've been using t for time to parameterize our lines. We don't want to stick with lines though. We're going to be switching to curves. And so time isn't always going to be our best thing, as you'll see. But any parameter that we use in the function will work as long as we keep the function smooth. A vector is smooth if the parameterization keeps the derivative continuous and not equal to 0 for all t on some interval I. So a smooth parameterization means smooth curve. And what does that mean for us? There are no cusps or sharp points. No sudden changes in the tangent vector. That's what we want. We want to keep that tangent, just like with regular functions, we want that tangent line to go smoothly. We want the tangent vector to go smoothly as well. So let's just take a look at an example. If we have x equals 1/7 y to the 7th power, using time, y equals t, we have x equals 1/7 t to the 7th. And so we have our vector function, r is 1/7 t to the 7th t, and r prime of t, take the derivative, we take it with respect to the t, bring the 7 down, we got 2 to the 6th, t drops down to 1. This does not equal 0 for all t. So r of t is smooth. It can equal 0 at a point, it just can't be equal to 0 for all things. A bad way to parameterize it, if we use y equals tau squared, x equals 1/7 tau to the 14th. When we plug in tau squared to y to the 7th, our vector with tau in it is now 1/7 tau to the 14th tau squared. We take the derivative and we get 2 tau cubed, 2 tau. So plugging tau equals 0 equals the 0 vector. My bad. A second ago I said we can have the 0 vector. That's not true. On a regular function, we can have a spot where the tangent or the slope is 0, but on the vectors, we need it to keep going. Okay. So just pictorially, what's going on with the function I just gave? X equals 1/7 y to the 7th is graphed approximately like that. Remember, we're doing pointers with our vectors, pointing from the origin. So R0 doesn't do anything. R1 points right here. R2 is over here. R3 is way over here. Notice the scale, 300s. These are massive jumps. Okay, I'm only going 1 time second, but we go from 18 to 312 along the x-axis. This is why time isn't always the best choice. We want to parameterize with something that is a little more consistent. On curved lines, it's always consistent. Time step is a distance step, but sometimes we want to keep that distance at a good steady pace. So rather than looking at time steps along the curve, we're going to look at distance steps. And distance steps along a curve. What's the length along a curve or an arc? Arc length. Yep, it's back. You thought it was going away in Calc 2. It's not. So in Calc 2, you had the integral from a to b of dx dt plus squared plus dy dt squared, the square root of that, integrated for dt. In 3 dimensions, we can jump it up to dz dt in there, and it doesn't change anything. It's still just the distance formula. We're integrating along it. That should look familiar. That's the norm of a vector. So arc length is the integral of the norm of a vector. Okay, that's arc length, and we're going to use that as a parameter. as you'll see shortly. We're going to choose a starting point. We're going to use S to represent arc length, like S equals R theta from trigonometry. And we want to have an orientation and direction like time did. So we're going to go from T naught, some initial starting value T, which is T naught, up to T. And then since we're using T's in the limits of integration, we're going to use a dummy variable U to do the actual integration. And then when we integrate, you'll see that each step gives us an equal distance along the line. Okay, this is 1 unit, the way I've got it set up. That's it for this section. Peace.